minute or two, but welcome to the Manufacturers Roundtable today on ground source heat pumps. Super excited to have you here. We have a great list of 5 panelists, all who are experts in the ground source heat pump or thermal network space. So looking forward to a great roundtable. With that, I'm going to quickly turn it over to Sean Williams, who is leads outreach for the California Energy Design Assistance Program. So take it away, Sean.
Hello all, and thank you, Noah, for passing it over. So just wanted to speak a few moments about the California Energy Design Assistance Program to start things off, also known as CETA. Um, CETA, the California Energy Design Assistance Program. It's the only statewide incentive program for new construction and major renovation projects here in California. Um, the purpose of the program is to promote electrification as well as decarbonization amongst the new construction and renovation projects. CETA does work in collaboration with project teams to reduce energy demand, consumption, as well as the carbon emissions. Through the program, we do serve commercial, public, high-rise multifamily, industrial, as well as agricultural projects that are located in the one of 4 investor-owned service territories, which would be PG&E, Southern California Edison, SoCal Gas, San Diego Gas and Electric. Okay. And so why participate in CETA? $1 million question, right? Well, a couple points here. First, for the project that you would like to enroll, you would receive a complimentary and custom decarbonization analysis that's tailored to specific project goals to help identify the most effective energy efficiency measures to implement. It's a great way to gain analysis of energy costs as well as paybacks, and of course, receive financial incentives to help offset the cost of these decarbonization measures. Um, Also, a great opportunity to demonstrate a commitment to high performance building practices and design. Okay, so speaking a little bit about the incentives, as you can probably pick up on, it's a free program, it's complimentary, and we do offer free design assistance, right, in the form of free energy analysis as well as a decarbonization analysis, which we strictly, act as a collaborator. We're brought on as a collaborator. Now, so speaking a little bit about the next portion, which would be the incentive. Um, we do offer 2 types of incentives through the program. First is a $2,800 design team incentive per project. And really, it's as a thank you, as participation, but it's also geared to offset the cost or the time that the design team will spend within the program. We only ask for 2 hours worth of live meetings from start to finish. So $2,800 is kind of geared to offset the 2 hours that we require through the program from start to finish. So the next is the measure package incentive. Measure package incentive. I can just speak on that real quick. And this is kind of the bread and butter incentive. It's based off of what the project is actually implementing, and we'll do a whole building analysis. So at the end of the day, we just like to review some of the building systems, get you credit for what you're planning on doing, and if there's any form of analysis that we can provide to the project, something you want to see, we can get a report going for that. But the incentive amount and check will be based on those measures after construction is complete. Okay. And so there's a couple. So within that measure package incentive, there's thousands of types of energy efficiency measures that could be incentivized. Some I'd probably say are low hanging fruit, and we have a comprehensive list of that. We can enroll the project and get credit for some of the basic things that are planning to be done. But then we also have what we call high performance measures, which is ties in great to the meeting today. So we do have a list of high performance measures on our website that you could view. a lot of which I'm sure will be discussed today. So the goal of the high performance measures is to exceed California's decarbonization standards and provide educational opportunities to explore use cases and best practices. Once again, full list on our website. You can just type in CaliforniaEnergyDesignAssistance.com. Okay. And last but not least, here's some quick contact information for all of those that have a new construction or a major renovation project, which we could discuss. There's my contact. Feel free to reach out. Once again, it's a free program, and we'd love to take a look at anything. And we accept projects from owners, developers, architects, government agencies. So all of sure on which are on the call today. So thank you all.
Wonderful. Thank you, Sean, and huge shout out to CETA for being a sponsor of this roundtable. Awesome. So we have a jam-packed roundtable agenda today. First things first, we had that intro, and thanks again, Sean. Then we'll have Will from Water Furnace talk about ground source heat pumps and kind of give some introductory language there about what ground source heat pumps are and some of the different applications. We'll have Matt Rash from MIA talking about water source considerations. Then we'll have Andrew Iliff from HEET talking about some of HEET's work on aggregating a bunch of resources for geothermal and kind of helping push the market forward with Think Thermal together. Then we'll have Stuart Yanow from Geotility talking about Orca Energy and making geothermal easy and affordable. And last but not least, we have Joselyn from Bedrock Energy, and she'll be talking about electrification and energy savings with geothermal and some advanced machine learning and drilling techniques. And then we'll wrap up with a panel question if time permits. Next slide. So yeah, a few of the overarching topics for today. We're going to discuss the benefits of ground source heat pumps, as well as some of the barriers for adoption. We sneak peek, we have a little bit of a quiz in a sec here about how many ground source heat pumps have been deployed, and it might be more than you think, it might be less than you think, but regardless, we're going to talk about some solutions to increase those numbers. We'll also talk about commercial building applications in addition to single family homes. And then also even touch on some multi-home solutions such as thermal networks that allow you to reach several different homes or even dozens of homes with basically an aggregated form of ground source heat pumps. And lastly, we're going to talk about some innovative technologies that allow ground source heat pumps to be deployed even in spaces with less room. You might think that ground source heat pumps need a ton of space, like a massive yard, in order to do the drilling and establish boreholes, but there's some awesome innovative breakthroughs that allow them to be put in a variety of locations, even in urban areas. Next slide. Yeah, so today's panelists, we have Stuart Yanow, who is the president of Geotility Geothermal Systems. Stuart is a certified geothermal engineer who has dedicated much of his time as an engineer to the advancement of geothermal systems. He is responsible for the design of some of the largest geothermal systems in Canada and the United States. We have Joselyn, who is the co-founder and CEO of Bedrock Energy. Bedrock is a technology startup helping real estate tap into clean heat from the ground right underneath their properties. With subsurface analytics and autonomous drilling innovations, Bedrock is dramatically reducing the cost, space, and time requirements of constructing geothermal HVAC systems. Then we have Matt Rash. He's a senior product manager, hydronics at Mitsubishi Electric Trane, HVAC US. He's a manager for the commercial air-to-water hydronics business segment. He's been with Mitsubishi Electric Trane since 2010, and he comes from a consulting background in the architectural and engineering community, where he's worked for 8 years as a mechanical engineer responsible for designing HVAC systems for commercial, healthcare, and institutional facilities. Then we have Andrew Iliff, Director of National Networks at HEET. He works with the HEET team to bring together communities, workforce, utilities, regulators, policymakers, and other stakeholders to accelerate the transition from gas to geothermal across the United States. And lastly, we have Will Lange. Will is the Director of Utility Engagement with Water Furnace. He's engaging with utilities, advocates, and policymakers. Will provides information and tools needed to succeed with heat pumps. He's also a graduate of the U.S. Coast Guard Academy with several tours on active duty and has 30 years of experience in advanced product design, development, and marketing. So next slide. We're going to turn it over here to our first presenter, which is going to be Will.
All righty. Great. 1 second. Let me know when you see it.
All right, I can see it.
Terrific.
Want to just go to full screen mode there?
Working. There we go. Takes 3 clicks now.
Yeah, it does
Okay.
indeed, but it looks great. Thanks so much.
All right, folks. We're going to start out easy. As was mentioned, I work for a manufacturer of ground source heat pumps. I'm actually at the headquarters building today, and I've got some interesting stuff to show you to get started. First of all, ground source heat pumps fall somewhere in this word salad of geothermal heat pumps, geo units, water units, all kinds of different stuff. If you stick with this webinar till the end, much of this will become clear and you'll understand it much better. First, I want to emphasize that there are ground source heat pumps for every kind of building, whether you're involved in the One Rockefeller Center conversion in downtown New York City, or if you have a small cabin getaway in the mountains of Colorado. There's a heat pump for every building and every type of application. And we're not unique in that at my company. All of our competitors offer a wide range of selections. So there's an industry-wide choice of different things. Just some real basics for those of you that are new to this. If you have an air conditioner on your house, you probably have something that looks like this outside, typically outside the master bedroom window. Don't ask me why. That's where they always put it. If you were to have a ground source heat pump, that unit you see highlighted there would become underground pipes. The unit inside your house would remain very similar to what you're used to now. Noah mentioned if you might have some preconceived notions about loops and, I don't have a big enough yard, or I live in California, or I live in Las Vegas. Don't sweat it. There are loops for every kind of application, every kind of property, whether you have a horizontal loop that's several hundred yards long, a pond, a vertical drilled loop, or even now, you'll hear more about this from Andrew Iliff about network geothermal. We got a little extra treat today since I'm at headquarters. I'm going to show you a loop. This loop is 34 years old. And do you see that out the window there? That's 34 years old. It's loops of pipe underneath that pond. We put them there underneath that ice 35 years ago, and they continue to heat and cool our building every day. We're at 72 degrees, whether it's 20 below zero or 100 degrees out. We have no backup electric heat. The pond does it all. So there are options for everybody. Moving on, there's always a bit of confusion when people say ground source heat pumps provide renewable energy. They do. You have to consider it a pump that actually pumps heat from the earth into your building, or from your building back into the earth. And that's where the renewable energy comes from. We use water typically pumped into the ground in a closed system like the radiator in your car, and then pumped back into the building. So that's how we exchange heat with the earth. When you think about the earth being 55, 60 degrees, 10 meters below the surface, and you think about the air outside going from maybe 30 below zero to 110, depending where you live, the earth is a much more stable place to exchange heat, and that's where the renewable energy comes from. Just a quick way to imagine that using air and water. If you were forging a piece of metal like a blacksmith and you wanted to cool it off, would you dump it in water, or would you dump the horseshoe or wave it in the air? Which would be quicker, which would provide better heat exchange? Most of you probably said water would be quicker and faster because water conducts heat better than air. That's where some of these extreme efficiencies come into play. Technology has changed dramatically. Both Water Furnace and our competitors have upped the game. We have inverter drive compressors, variable capacity airflow, water flow. Everything now operates on an as-demand basis if you choose to buy an inverter type heat pump. We can control these units from a cell phone in a pickup truck in Paraguay or from the beach in California. You can see everything there is to see on these units remotely. We monitor them every 10 seconds. We do active dehumidification. That's something new to the industry with reheat coils, and we now do vapor injection. We have caught up to and perhaps even surpassed European technology in heat pumps with vapor injection, which allows very low temperature performance for ground source heat pumps. They're the original cold climate heat pump. And you can see a heat pump here, an air source heat pump covered with ice versus a ground source heat pump that would reside inside a building and is generally unaffected by the weather. No part of a ground source heat pump is typically exposed to the ambient weather outside the building. It's either underground or inside the envelope. For that reason, they last typically twice as long. And the underground loops typically last over 100 years. It's the same pipe that the gas company uses and depreciates for 80 plus years. So it's a long-term solution. So when you think of a cold climate heat pump, we've been there for 40 years. And when you think about extreme hot weather heat pumps, the same would be true. So how do I know that? Well, if this is directly downloaded from the AHRI database, which is where all manufacturers register their equipment by law, which is certified by the Department of Energy. These are the 26 most efficient air source heat pumps in the world are listed right here on this website. And I pulled them out and they're highlighted the EER, which is an energy efficiency ratio for cooling, and COP on the right for heating. Remember, these are the best of the best. And in green, I've highlighted the EERs for the best EERs out there among the best, and their COPs that go with them. So kind of memorize those numbers if you can. 13-ish for the EER. This is that ground source heat pump I showed you a picture of a few minutes ago. These are the COPs and EERs related to that unit. And you can see that it goes as high as 54 and as low as, worst case scenario, as low as 17. And if you think back, we were talking 13.8 for the best of the best of the best in the 5-ton category. So extreme efficiency as a result of being ground source. And those are just some numbers that you can put in your back pocket. If you choose, you can go to this website. Every manufacturer in our industry has a website where you can look up the potential savings. This was a house I picked of a coworker, and that house would stand to save about $2,000 a year by converting from a gas furnace and an electric air conditioner to a ground source heat pump. That's pretty typical for a 3 or 4 bedroom house across the United States, about $2,000 a year in terms of how much savings you should experience. I encourage you to look up your own house and check it out if you want to do that. But think about its energy savings, its carbon production savings, its repair savings, and of course, utility savings. But those are just laboratory testing data numbers, right? Who cares, right? Everybody can talk about your MPG may vary. But so let's take a look at Minnesota, the 3 coldest hours of the last year in Minnesota and the 3 hottest hours. So these are extreme temperature performance ratings. actual observed temperatures. You see in the top left box, Duluth, Fargo, Minneapolis, Sioux Falls, and St. Cloud. And inside those dot plots, you can see where they came out in terms of kilowatts required per nominal ton of capacity. And the way that comes out is 360 readings over the course of an hour, every 10 seconds. So it's actual kilowatts measured of every component in the system, totaled up and plotted against nominal capacity. So these are 3-ton units, 4-ton, 5-ton units. And the number you see on the left in the first graph, for instance, the red line goes through at about 0.5 kilowatts per ton of capacity. None of these units in the wintertime readings in Minnesota used any electric strip heat backup. That's pure heat pump operation. And of course, the same is true in the summertime, where you see EER really in excess of 36 for those 100 and something units that we measured. You can see on the left the map demonstration of where those units were located. And those are actual performances of each one of those units. This is a kind of a heat map. This doesn't represent all ground source heat pumps. It's just a small selection of customers that chose the advanced controls that we can monitor and troubleshoot and where they're installed. You can see throughout the Midwest where the electrical cooperatives have really pushed ground source heat pumps over the years. And in the Northeast, where you see extraordinary rebate programs in excess of $10,000 and even $20,000 per home per heat pump. So this graph continues to march westward. Still have a lot of opportunity, you can see in California, but that's why we're here today. We can look into every one of these houses and see what their annual rolling 12 average utility consumption was by kilowatts or by dollars. We can adjust the kilowatt cost per hour. And that's what it looks like, say, in Buffalo, New York, Rochester area, for heating and cooling. At an annual cost of $375, that's extraordinary as compared to, that would be a monthly cost, for instance, if you were using heating oil or propane.
And just a heads up,
really,
Will, 2-minute warning here.
Okay, just wrapping up. This is what your controls display might look to a homeowner. This is what it might look like to a technician sitting in that pickup truck in Paraguay troubleshooting your system. He can see everything he needs to see or she needs to see on your system from a remote device. And you can figure out, what's going on anywhere at any time on all of those systems. So I guess the message is this is not your grandparents' heat pump. Things have changed. If you have any questions, you can screenshot me here or look at the recording. And my job is to help utilities and advocates and groups like NOAA's New Building Institute come up with ways to explain this to people and find the savings and move the deployment of these heat pumps forward. Thank you for your time. All set.
Really, really excellent, Will. That was a great overview. And so we did have a question pop up in the Q&A. In rocky areas where there's solid rock just below a building's foundation, are geothermal heat pumps a good option? Also, what's the typical depth for installing pipes in these systems? I'm asking because, for example, in Victoria on Vancouver Island, the rocky ground made it tough to lay natural gas pipes, which is why some areas don't have natural gas.
I think Stuart's the best person to answer that question, but we love rock. Rock provides a tremendous heat transfer potential. Drilling 300 feet of straight granite in Maine is terrific, or caliche rock in Arizona. Once you get down 30 or 40 feet, it's kind of all the same. But rock is good and sometimes a little harder to drill, depending where you are. I'll let Stuart talk about that when he comes up, but rock is your friend.
Awesome. Good to know. Cool. Love myth dispelling whenever we get that. Perfect. Well, thanks a ton, Will. That was really great. And if folks have other questions based on Will's presentation, feel free to put them in the Q&A and Will will take a look at those. Thanks again. Sweet. Well, next up is Matt Rash from MIA, talking about water source considerations.
All right, thank you. Can everybody see my screen and hear me okay?
Can indeed. Yep.
Okay, all right, great. So yeah, we're just spending a little bit of time talking about water source VRF and the VRF realm of things in terms of commercial applications and where this technology can play and be advantageous in this geothermal realm. Again, this is more focused on the commercial segment where we play with Mitsubishi variable refrigerant flow water source gear. And there's quite a few other manufacturers that are in the market as well. But these are some of the major considerations and capabilities that this type of technology can offer. All right, so we're going to walk through that in a little bit of detail. So our current product is called the L generation water source. You can see an image of what these modules look like. They're meant for indoor installation, obviously. Two water pipe connections on them. They utilize a brazed plate heat exchanger. I'll talk about that in a minute and some of the considerations for that. But these are typical size capacity ranges that you have to work with. Again, these are meant to interface with variable refrigerant flow refrigerant-based systems. So these modules are exchanging heat, absorbing or rejecting heat to a refrigerant loop that then sends that to individual refrigerant-based fan coils, but their heat sink is a water side heat sink. So we have two variations of this available. And again, this is fairly common among different manufacturers, but we have something that's called a heat pump changeover system up to around 30 tons. And then we have something that's called a heat recovery system up to around 28 tons. So much larger module size than conventional water source heat pump layouts. So again, as I mentioned, you have a water side heat sink that would, in this case for geothermal, be your geothermal well field. Typically, it's exchanging or rejecting heat to that. Also on the building side, within that building condenser water loop, you're exchanging, rejecting, transferring heat among the modules in the building across that common loop. So that's your common kind of highway exchange system for heat recovery. With the changeover system, the WY, all of the individual fan coils on the respective module have to be in the same mode at the same time. Again, those are all fed with refrigerant, and there's changeover methods for when they all go to cool or all go to heat. We're not going to really talk about those details, but just know that is one limitation of these systems. They all have to change over together, but any excess heat absorption or rejection is shared on that condenser water loop. So taking things a little bit farther, as I mentioned, we have a heat recovery VRF system which allows individual zone fan coils to operate in different modes at a given time, and then also subsequently can reject or absorb heat and share heat across that common condenser water loop. So this is really kind of the best of both worlds. You've got optimized heat recovery on the refrigerant side, and then secondarily on the condenser water side. So because you're dealing with larger modules and they're serving multiple zones versus individual zoned water source heat pump systems, you'll often find with these systems, especially in the shoulder seasons, that your total peak compressor energy is reduced because these modules work to meet the dominant load, not the sum of the peaks. So that's one advantage that you have with this, and that can kind of optimize that geothermal design. As I mentioned, this product is rated for geothermal. It can often be applied with cooling towers and absorption with boilers where needed in hybrid strategies, but perfectly suitable for closed loop, and I'll highlight that closed loop geothermal type applications. So vertical bore well fields, closed pond loops, perfectly fine. Anytime you get into a pump and dump type application, there has to be a separation with separation heat exchangers. We need a closed, chemically treated, sealed loop for these systems to operate with. You can see typical correction factors that come into play with this gear. in rating conditions. So again, this is based on Mitsubishi, but you'll find other manufacturers are similar. So we actually have guaranteed capacity data up to 113 degree entering water temperature, and then all the way down to 23 degrees. And you can see these capacity corrections in cooling, for instance, only about 86%. So about a 14% loss only at 113 degrees. And then on the heating side, you still have about 65% of your nominal, even at 23 degrees. You do have to consider glycol with these systems. For our equipment, anytime you're going to operate below 50 degrees, require glycol for freeze protection. So that's obviously important to be mindful of early on in the design. This type of technology is well suited to centralized plant installation. It offers a very compact footprint. You can stack these systems with field provided racking. We also see a lot of projects where these are installed in small utility closets on every floor, for instance, and you can minimize the number of risers and the amount of water piping in a building by doing that. So different ways to apply that depending on where that makes sense logistically for your particular building. Some minimum piping provisions you want to be careful of and mindful of with this product. As I mentioned, it's braze plate technology. So it can be prone to clogging if the loop isn't properly maintained and flushed. We do recommend a 60 mesh strainer on these braze plate heat exchangers, and then obviously some means of balance and flow switches. And there's other things that can be done to accommodate variable speed hydronic pumping on the condenser water side. We kind of outside the scope of this presentation, but we have information on that available. I think one of the bigger advantages with this product with geothermal is where you can consider hybrid type geothermal systems where you have towers to help supplement that geothermal loop. That kind of drives down the cost and the size of that well field in many cases. We always get a lot of questions on how do we size for diversity or partial heat rejection or absorption if you want a backup boiler or a backup tower. And these are really basic formulas, and these apply really to almost any manufacturer's geothermal equipment gear. It's basically just that diversified block load that really has to come from the engineer of the record for your tower rejection, and then that block load divided by the EER multiplied by 3.412. This component here really is just your heat of compression. So it's your block load, whatever that worst case is, plus the heat of compression, plus some pumping energy that's imparted into that condenser water loop. For heating diversity, if you're going to size with a backup boiler, you would need to know that peak load, and then you can subtract off the heat of compression component. So that's really just your block load divided by the COP. And those values, the EER and the COP in cooling and heating, can be obtained from the manufacturer. Another thing to consider is why use water source VRF versus traditional VRF if you're familiar with that type of product. So this is more important when you start looking at high-rise applications because of limitations on refrigerant lift, the elevation differentials that these systems can accommodate. Cold climates, where you have backup heating needs in the zone, especially with electric, not only is that costly, but it can introduce comfort issues because there's a hysteresis there with regard to operating backup heat with air source product. And then really, which is really the subject that we're focused on here today is ultimate efficiency. And that's really going to be in that geothermal realm, and where projects are mandating that water source VRF again brings that capability to achieve that with some added benefits with optimized heat recovery. These are some comparisons for how these water source VRF systems compare versus air source. This is a typical model that was done for a Cincinnati 34,000 square foot office building. And you can see full geo operating costs being the lowest at around 37,000. You can see the rates this was based on 10 cents a kilowatt hour and $1.10 a therm. If you were to do this with full boiler tower type design, it was up closer to 47,000. And if it was air cooled VRF, traditional VRF, it was 43. So this largest operating cost with boiler tower, that's really coming from mostly the heat of absorption, because that's really all coming from the boiler that's present on the project versus obviously geothermal. you're sourcing that heat from the ground. So it really is your optimal system. Here's another example with a different rate structure. This is 12 cents a kilowatt hour and 80 cents a therm. And again, you can see there's some dynamics there between the rates of gas versus electric, but geothermal water source VRF geothermal is always going to beat out the other two options. So again, some of the bigger advantages with water source VRF, and this isn't necessarily exclusive to this type of technology, but wide temperature range up to 113 degrees. Like I mentioned, this can play into well field sizing, reduce compressor quantity and maintenance because we don't have to have individual zoned water source heat pumps. To provide an equivalent level of zoning, we can reduce the number of electrical feeds and number of points of maintenance and really get the compressors outside of the occupiable space in most cases. So ease of maintenance, reduced electrical feeds from main switchgear or panels. Again, we offer single module units up to 20 tons. I didn't mention that before, but up above that when you start twinning modules together. So again, more flexible connected capacity versus air-cooled VRF. If you're not familiar with traditional VRF, that may not mean as much to you. And again, removal of the need in most cases for auxiliary electric heat out at the zones.
Matt, a couple minute warning here.
Yep. Okay. I'm gonna jump ahead a little bit. One thing I would know is geothermal well fields, they tend to be cooling dominant, and that's just because of heat of compression. All right, so if we had a balanced building in terms of number of BTUs of cooling versus heating throughout the year, because of that heat of compression component, the well fields tend to be cooling dominant, even in more northern climates. So here's an example with a 20-year well field profile simulation on year 20 for a school in St. Louis. And you can see if that 20-year peak temperature was limited in this design to around 93 degrees, you have 117 wells, 30 feet deep, 20 foot on center. If we can increase that 20-year limit, and that's typically how a lot of these well fields are designed to not exceed a 20-year limit temperature. If you can allow that to bump up to 106 degrees, you can reduce that to 85 wells. So that's close to 9,600 feet of borehole savings. And again, I'll let some of the other experts maybe speak to the costs these days, but certainly $18 to $20 a bore foot, that could be a significant savings. There's to combat that, as I mentioned, I think looking at hybrid VRF is very advantageous. There's been studies that have been done with the DOE as well as other entities looking at comparisons of full geothermal to hybrid. So this is for a 14,000 square foot office building. And they looked at this in Tulsa and Houston, Texas, and really for very minimal impact, if not in some cases, depending on how that backup tower was activated in the project, the hybrid case was a lower operating cost, right? Maybe slightly higher in this case 3, but depending on how they operate the backup tower. And so if you look at that, they kind of summarize this in terms of number of boreholes and total project cost, even with the towers. And again, with that well field cost being in that $18 to $20 a bore foot range, again, that may be a little bit higher now with market conditions. It's a significant cost advantage, and oftentimes more efficient to operate because you're not pushing the limits of that well field, especially in cooling dominant applications where that temperature tends to creep up over time in the summer months. So just something to think about. You can see here their 20-year period max temperature in the simulation for a full geothermal was around close to 97 degrees, and it was actually lower in 2 of these hybrid cases. Actually, all 3 of, right? And this is for Houston, Texas. This is for Tulsa. You can see generally lower across the board in terms of that peak 20-year temperature. So obviously you've got the added cost of the towers, but generally that is dwarfed by the cost of the additional wells. So looking at a hybrid strategy can be advantageous to bring the cost of these systems down and really optimize the effectiveness of them. And really the goal should be to have that balanced well field, dump just enough heat into it for what you need to take out for that winter operation and keep it balanced and do that efficiently with optimizing upfront cost. So again, that's kind of a lot in a short period. If you're interested in this product more, I'll just end with this. We do have some application notes. If you go to mylinkdrive.com, under commercial, there's application notes for this product, both covering the product in general and water source VRF, variable flow, which we didn't really have time to talk about here. But take a look at those resources, and there's always staff and sales support on the Mitsubishi side to help with designs, if you have interest in this. And of course, we'll share this presentation as noted. That's it.
Great. Thank you, Matt. That was awesome. Really love getting all the cost breakdowns and performance and everything. So yeah, just a quick intermission here. We're gonna just answer a geothermal poll question. So out of the 120 plus million homes in the US, how many do you think use geothermal heat pumps? So 0.4 million, 1.3 million, 3.1 million, or 5.7 million. So based on what you've heard so far in terms of costs and adoption and everything, just take your best guess and we'll reveal the answer shortly. Sweet. Well, yeah, thanks again, Matt. It looks like, oh, there are a couple of questions popping up. So first one is, how are the tax credits impacted with a hybrid system?
Yeah, I don't have details on that specifically. Maybe some of the other panelists could offer insight there.
Yeah, no worries. And then are there any environmental implications of using ground source heat pumps and water bodies as heat sink or stores for long periods of time?
Yeah, I mean, I think that's some of the other panelists could add insight there, I'm sure, but that's geographically and municipality kind of dependent and where
Totally.
that's enforced. Obviously, there's concerns of that, but keeping that well field balanced, I think, as I mentioned, with hybrid type applications, you can minimize that impact over the life of the building, and achieve lower operating costs in many cases and lower upfront costs. So I think there's more intelligent ways to balance that out to minimize that impact, because as mentioned, well fields tend to be cooling dominant, meaning they dump more heat than they absorb. So you can combat that easily with a hybrid strategy with a backup heat rejection device.
Sweet. Okay, awesome. Well, thanks again, Matt. Really appreciate it. And to answer our poll question, the correct answer is 1.3 million. So that's second option. So looks like about 31% of people guessed correctly. So it was actually a little higher than I thought it would be as well. So that's kind of why I put that 0.4 million. See if I could throw some folks off, make it a little harder. But nice job on the poll there. And with that, I'll turn it over to Andrew from HEET.
Thanks, Noah. Hi, everyone. I hope you can hear me all right.
Can hear you
Let
just
me
fine.
call up my slides and is that coming up? Oh,
It's loading up.
all right. Well, in the meantime, let me say I am not an engineer. I'm not even a manufacturer. So I don't know quite how I snuck in here. Noah must have left the door open. It's saying my screen sharing is paused, but when I hit resume, nothing happens. That's interesting.
Do you want to just stop sharing and try again?
Yeah. When I stop sharing and try again. Is that better?
Perfect. Okay, there we go.
Okay,
Awesome.
great. So hi everyone. I'm Andrew Iliff. I direct the policy work at HEET. HEET is a nonprofit working to drive an ethical and efficient thermal transition. In practice, what this means is we focus on accelerating the transition from gas infrastructure towards clean and low to zero emissions thermal energy based around the use of ground source heat pumps. So that, I suspect, is why I'm here. You be the judge as we get through here. So, my slides say think thermal together. What does that mean? This is the world mapping out increases in temperature. It may be familiar to many of you. We're used to thinking of this as a real challenge, and it is one of the greatest challenges we face. We like to think it's also an opportunity because that is a lot of thermal energy that we can tap. And this is a quote from the International Energy Association just a few months ago, saying the technical potential of geothermal would be more than enough to meet all heat demand in Africa, China, Europe, Southeast Asia, and the United States. And just to say a little bit more about that opportunity. So this is just a map of estimated energy consumption in the United States. And the thing that I want to draw your attention to is that arrow in the top right that just shows rejected energy, meaning energy that is not being used for anything productive. We think we can do better, and we think ground source heat pumps are a key component of the way to get there. So Will and Matt already covered this pretty much, but I feel like it's really important when we're talking about geothermal just to do the sort of throat clearing about the type of geothermal that we're talking about. Matt and Will spoke about that middle category, heating and cooling with a geo heat pump. I'm going to talk mostly about utility scale heating and cooling. So goes by different names, geothermal network or thermal energy network. All geothermal energy sources provide stable, clean, non-intermittent energy. I'm going to spend my time talking about the advantages of thermal energy networks. This is just a little bit about heat and how we work. So we work with the full spectrum, full ecosystem of stakeholders engaged in buildings, which is to say almost everyone. We work with those stakeholders to identify leverage points for innovation. When heat actually has a long history working on gas leaks, gas leak detection, gas leak mitigation. And then as we started to think about kind of how we could build a better clean energy system, we engaged with stakeholders, we thought about the requirements. This is the list of requirements that we came up with. And I'm not going to go through them all because it's a long list, but I just want to impress upon you that this is a long list. But we think thermal energy networks come through. You be the judge. Happy to discuss this more later if there's time. So thermal energy networks, this is a little like what Matt just presented, but at a kind of neighborhood scale. Fundamentally, there's three components. There's your buildings at the top there, each of which has a ground source heat pump, geothermal heat pump, as Will said, same. A distribution system, this is the sort of key technology and a little bit like what Matt was talking about. It's basically like the Framingham project that I think Will referenced. In that instance, it is just a circular pipe carrying water plus a little bit of glycol that is probably not strictly speaking necessary in many instances. And what that does is it moves thermal energy around using water as the medium from thermal sources to the buildings that need it. And then the last component that I'm going to talk about in probably the most depth is these thermal energy resources. So Will already spoke about geothermal bores as a thermal energy resource and open water as a thermal energy resource. We think there is an entire universe of opportunities here. Wastewater, industrial waste heat. I'm going to talk about some others. So that's just to kind of set the stage. Again, so one of the key features of thermal energy networks is you get even greater efficiencies than the incredible efficiencies that Will and Matt were talking about. Why is that? Because you get synchronous load cancellation, meaning that building in the top, sort of second from the top right there, that is rejecting heat. Let's say it's a cafe or a bakery or something like that. So it has some excess heat. That heat goes into that purple pipe, that's the loop, and is immediately available for neighbors to use that heat using their ground source heat pumps. There is no generation required. You just move thermal energy from where it's rejected to where it's needed. And you can do the same thing depending a little bit on your subsurface features over the course of a year with different seasons. So I live in Massachusetts where we have hot summers and cold winters. So in summer, when we're rejecting heat, that heat can go down into the subsurface And essentially, we can use the subsurface as a thermal battery so that in winter, when we want to heat, we can just pull it up from the surface to heat our buildings. And that's how thermal energy networks get these unprecedented efficiencies. Why does this matter? For a lot of reasons, some you might not be thinking about. So as you may know, the United States currently has a summer peak for electrical demand. That's primarily driven by building cooling, so when we all turn our air conditioners on. But as we start to electrify further, and in particular electrify heating, that is going to change pretty radically. And how radically depends very much on the technology we use. So this is what we call the Falcon curve. Some of you used to duck curves, better get ready. This is much more dramatic. So this is just mapping out the electrical grid demand, peak electrical grid demand over the course of a year, depending on adoption of different electrified heating sources. So if you use electric baseboard heating with a COP of around 1, you get that red curve, and you can see that just puts, what does that do? It sort of more than trebles current peak demand in the winter. Air source heat pumps are great, but as I think someone showed earlier, they have a COP of around 2. So we're still gonna, and particularly in those cold winter days, we're gonna have very high peak demand. Ground source heat pumps, as we've talked about, much, much more efficient. And network geothermal, because of this synchronous load cancellation, the ability to use the subsurface as a thermal battery, have even greater efficiencies. And so this allows us to minimize the build out of our electrical grid. This was actually modeled by the Oak Ridge National Labs. And in a report that came out December 2023, the text is kind of faint, but the citation is down there. And the key points are here. So 38% reduction in transmission lines, 13% less generation needed, which is going to show up in wholesale electricity rates, $19 billion a year in fuel cost savings, and I already mentioned cheaper wholesale electricity. So this is a big deal, not just for customers, but at system scale. And that's the scale where HEET really is thinking. And this also, and that scale is central to actually doing efficient and kind of thoughtful electrification. So my boss was actually just talking to folks about this in Pakistan, and Pakistan is actually in 2 forms of utility death spiral, where they've had a lot of unplanned electrification. So people are putting out solar panels and increasingly batteries and getting off the electrical system, which means that those who remain on the utility electrical system are paying more and more and more. So that more people are getting off the electrical system, raising costs further. Same thing is happening with the gas system. So a thermal energy network actually allows us to electrify at scale in a planned, systematic way. So that green line there, that's just little street segment that electrifies. And then you can move back further out of the gas system and electrify part of a neighborhood and go all the way out and potentially retire that gas infrastructure as you electrify an entire neighborhood or municipality. This also has really important features for the utility deployment, because it can potentially stabilize rate bases. So if a utility builds a thermal energy network, like the project in Framingham that was built by Eversource Gas, we think there is a pathway where the gas at the outset, when the gas system is just beginning to build thermal energy networks, the gas system can essentially, the existing gas rate base can in some instances subsidize the development of thermal energy networks, so that in a place like Massachusetts, as we're looking to retire some of the gas system, the thermal energy networks will then be able to cross-subsidize the gas system over time, stabilizing rates for everyone. And this is, I said I was going to talk some more about this. This is the next frontier, all these different thermal resources that really have not yet been brought into play. So wastewater is a major one. There's a hospital in Toronto that's being commissioned where 85% of its energy demand is being met through wastewater. Wastewater is an amazing thermal resource, actually, because it has so much heat that you can use to provide heating. You can also, in many instances, reject heat into the wastewater line, so you can have a bidirectional energy resource. Subway heat recovery. I love this one. This is a picture from a journal article about subway heat recovery that shows a sort of purpose-built capillary heat exchanger in a subway tunnel. But you can also do things like put a heat exchanger in a ventilation shaft to just capture the heat that comes through subway lines. Data centers, everyone's favorite topic of conversation in the energy world. This is actually just modeling installing heat pumps into an existing conventional air-cooled data center, which would be great. There's increasing moves to do liquid cooling for data centers, which would provide a much more dense and kind of accessible thermal resource. So that's an area that we get very excited about. Water source we've spoken about a little bit. Here in Boston, Vicinity Energy is putting a heat exchanger in the Charles River to provide low carbon steam to its customers. And this is that boiler. They haven't actually put the heat exchanger in. That's going to happen in the next couple of years. And so what does this look like in practice? We can network together all these different thermal resources depending on what's available where you are. And so this is just that kind of more schematically. So many of these you can see are sort of bidirectional, but a data center on the left there rejects heat year round. Boreholes you can use as a heat source in winter and a heat sink in summer. And then there's these cool things like swimming pools. There's a thermal energy network that's been in operation at the Colorado Mesa University for more than a decade. They use their Olympic-sized swimming pool as a thermal battery. You can reject heat into the pool, raise the temperature ever so slightly, and then draw down that thermal energy when you need it.
Andrew, 2-minute warning here.
Great, just wrapping up. Again, this is that list of conditions that we set out with. Happy to talk about that more. And just to say a little bit about the national landscape. So late last year, California joined this list of 8 countries with legislation basically enabling a pathway to build thermal energy networks at utility scale. We're very excited about that. We're working with folks, with commissions, with advocates, with utilities to help advance people down that pathway. Speaking of utilities, this is a map showing the Utility Geothermal Network Collaborative, which is a group of gas utilities that meet regularly to discuss opportunities and challenges in this space. These companies represent around half of all US gas customers. And this, to get back to the International Energy Association, these are some clips from a video produced that was shown at, I think, COP24. COP29 by the International Energy Association. I highly recommend it. It just talks about the potential of geothermal energy. And with that, I think, oh, yep, that's my last slide. I encourage us all to think thermal together. I hope I get an opportunity to answer some questions, and thanks for your time. And please feel free to reach out.
Wonderful. Thank you, Andrew. Loved all the graphics. That was really great. I loved the breakdown of the different types of uses of thermal energy. Really exciting stuff. A couple of good questions here. I guess just one is a clarification. Can you clarify, is the thermal energy network replacing the gas infrastructure or repurposing it?
So there's a couple of different ways to answer that. Sadly, so far, it is not possible to run water through old gas pipes. There's a range of reasons. In many places, those gas pipes are actually quite leaky. They're also sized wrong for a thermal energy network, and you would have to kind of, because you are creating a closed loop of a particular size, you can't use the same gas pipes. But the really interesting question is around the potential for thermal energy networks to essentially make the gas system redundant and allow you to retire the gas system. This, depends a lot on your regulatory environment, depends on, your state's emissions goals, things like this. In Massachusetts, we have an extremely active Department of Public Utilities that has essentially said in its Beyond Gas order from December 23 that the gas system has to reduce its emissions pretty radically. We are supposed to be net zero by 2050. And so the DPU says in that order that it views geothermal networks as the most promising technology to do so.
Wow. Okay. Cool. And then another one was, Do you find that utilities are often the entities that are initiating these types of projects?
This is a really interesting question. So I think the way that we think about it is that utilities just have they're sort of off-the-shelf solution. So thermal energy networks require a lot of upfront infrastructure, a lot of capital expenditure. This is exactly what regulated utilities do already. They build big infrastructure and they get cost recovery over decades. So we think that it's not that we think gas utilities are the only people that should be allowed to do this, but there's a sort of elegance to gas utilities doing this. It can, as I say, it can help stabilize the gas rate base, which is good for customers and good for the integrity and the safety of the gas system. So even in Massachusetts, even if we were to retire the gas system, as fast as possible, we're going to continue to have gas infrastructure operational. And we need to make sure that that gas system, as long as it exists, is working safely and is leaking as little as possible. I haven't even spoken about workforce because I've been trying to move quickly, but there's another advantage where gas workers already know how to lay the kind of pipe that we use in thermal
Yeah.
networks. They have exactly that expertise. So we like to think about gas workers, fixing, maintaining gas pipes one week and then laying new thermal pipes the next week and just being able to go back and forth.
Great points, Andrew. Yeah, no, it makes a ton of sense with that transition there. But sweet. Well, it looks like some more questions are popping up, but yeah, if you want to answer them in the chat when you have a sec,
I'll jump
Andrew,
into
that
the
would be
chat.
awesome. Thanks again for your
Thanks, Aaron.
presentation. Okay, perfect. Well, next we have Stuart from Geotility.
Yeah, thanks, Noah. Hello, everybody. So my presentation, I'm going to focus a little bit on kind of expanding on what previous presenters have discussed. So I'll be talking a little bit about what our company does. We're a private company that does geothermal installations. We are also a geothermal utility provider specific to geo. So kind of taking the next step and showing what's being done through case studies and in the current market. So let me just pull up my presentation here. Okay, can everybody see that? I'm assuming so. Okay, so let me just a brief introduction. Actually, let me minimize this. A brief introduction about what we do. Let me start with myself. I'm a mechanical engineer. I've been with Geotility Orca, our group of companies, for 19 years. Currently, the president of our company. My background is in designing HVAC systems. So I used to work for a large consulting firm, designing all sorts of HVAC systems, and then focused on or gained knowledge specifically in geothermal, geo-exchange, again, whatever we want to call it. The new term that I'm trying to use is geo-exchange. So I'm trying to convince people to use that term. I think that's a little bit more appropriate. But so yeah, back to started designing geo-exchange systems about 25 years ago, and then switched to the contracting side with Geotility. Now, our business kind of has two main silos or different streams of business. One is our construction side. So within the Geotility umbrella, we install geosystems, sometimes as a design build, sometimes we design it, sometimes it's they're bid spec projects. And we install anything from small single family residential installations up to large, and you'll see in my, I'll bring up some projects that show some very large commercial projects. The other vertical in our business is the utility side. So our geothermal utility business, we call it Orca Energy in the US. On the Canadian side, I am Canadian. I reside in British Columbia. Our Canadian utility is called TerraSource Utility Services. Now, the reason we started the utility business about 20 years ago was because of that large upfront cost. The capital cost of installing geosystems is primarily related to the ground loop. The incremental cost has historically always been adding boreholes, or if you're doing horizontal systems like Will showed, or lake ponds, that's an incremental cost. Now, if you're doing hybrid systems, which I'm a big advocate of, I've been designing hybrid systems for 20 years, so I fully support everything Matt was saying. There's the economics change a little bit, but fundamentally, the cost of that ground loop is the major barrier to mass adoption of geosystems. So we set up our utility business. In terms of what we do company-wide, we kind of cover the gamut. We've been involved in all sorts of projects, you name it. We've kind of seen it from public to private. We do construction, we do the utility side. As I mentioned with Orca, the intent with Orca is to offset that initial capital cost of doing the geosystem. So we design, build, and own geothermal assets. That generally means that we own ground loops. We own ground loops around the nation. We have customers around the US. Our focus has been primarily on residential master plan communities. We do have commercial projects as well and expanding that quite rapidly, but our focus has been primarily on the residential side because that's where we saw 20 years ago is the cost of the ground loop, excuse me, is the main challenge. So we fund 100% of the infrastructure on the ground loop side. So essentially, if you're a homeowner in one of our communities, you didn't pay for the ground loop, but you do pay for access to that ground loop. And our utility is set up such that you're paying the same fee in year 10 as you would in year 1. We do have a CPI increase every year, so our rates do go up by CPI, but that's it. We don't increase based on utility rates. We don't increase based on market conditions. Once we've installed the system in the ground, then our rates are constant and they're fixed in perpetuity, which is the reason why we say we create a stable thermal energy to the home. So again, some previous presenters have touched on this, but at a high level, really high level, why would you choose geothermal? Well, let's look at it from a homeowner perspective. If we're talking about new buildings, the homeowner has the benefit of, as Will mentioned, no outdoor equipment. That's a real driver. Here's a picture of, we like to show this one. On the left is Utopia, and on the right is what your condenser-filled backyard would look like if you didn't have geo. And in fact, a lot of the new developments that we're looking at, that is the single biggest driver for going with the geothermal utility option. A lot of the developments we're doing now are townhome developments where you have perhaps 1,000 or 1,500 square foot home townhouse. Your backyard is probably quite small, limited outdoor space. And it's nice to be able to remove that condensing unit or that heat pump from your backyard so you can enjoy the backyard a little bit more. And then some other benefits, the financial benefits. We show when we're looking at a community how the long-term energy saving, there are long-term energy savings to the homeowner, especially when you take into if you look at it from like a life cycle cost or a total cost of ownership over a certain duration, let's say 20 years. When you look at the replacement cost of heat pumps and you look at the lifespan of a geo heat pump versus a conventional air source or condensing unit, there are definite financial benefits. The environmental benefits, I don't need to speak to that. It's clear if you could displace fossil fuels with electricity, especially if you're in an area that has renewables, then your carbon footprint is reduced dramatically. From a developer perspective, and developer, I mean a land developer who's developing lots, selling lots, or building property and selling them. The benefits are clear in terms of the initial CapEx that they would have to expend on putting in geo is removed because we take that on. There's a marketing advantage by being able to go geo and then some of the other benefits on the screen here. So this, from a commercial aspect, this would be reclaiming rooftop space. You can get rid of rooftop units. Perhaps if you're doing a hybrid, you might have a cooling tower off to the side, but you can certainly regain a lot of commercial real estate by going with the geo system. The concept of the residential outdoor space beautifying and all of that applies to commercial systems as well, and there's more of an economic benefit by having usable space. Okay, so I'm just going to go through several projects. So the intent here is to show the group what is being done in the market today. Some of these projects, the first group of projects I'm going to show you are not under our utility model, but they are geo projects around the country. So just trying to give you a bit of a cross-section of what's being done across the US right now. So firstly, the Microsoft campus. Some of you may know Microsoft's world headquarters is located in Redmond, just east of Seattle. They Microsoft made what word am I looking for? They made a statement that they wanted to go carbon negative. And carbon negative is a kind of a weird concept, but the intent there is they wanted to offset all of the carbon that the company has emitted since the company's inception, which is mid 80s, let's say. So as part of that, when they were redoing their campus, they were doing a redevelopment of their main campus. They decided to go zero carbon, 100% zero carbon. So as part of that, they decided on a geosystem because, frankly, if you're trying to scale, and this is an important comment, an important thing to take away, if you're trying to provide a zero carbon system at scale, so think about those thermal energy networks, geo is really the best and the best technology to accomplish that. Going with 2,000 to 3,000 ton air source heat pumps is really challenging, hard to find space for that. This system happens to be a hybrid system. There are some electric boilers for peak loads on the heating side, but it is primarily fed by the geosystem. So we installed 900 boreholes to about 550 feet deep on average throughout the campus. And this was completed a couple years ago. And actually, as a result of this, the project itself won the ENR, which is Engineering News Record Project of the Year in 2023. So this is what the campus looked like prior to the project. And then hopefully this comes through. They essentially took down 100 acres of site and then built a whole new campus on top of that. So if you look at this picture, you could see there's some baseball diamonds. There's actually a cricket field and some soccer pitches, or a soccer pitch. And the geo field is underneath all of that. And this is what it looks like right now. So an example at large scale, what's being done. And we're seeing this technology or this type of approach being applied to colleges, universities, and campuses around the nation.
Quick 2-minute warning here.
Okay. Next project, Lulu Island District Energy System. This is in the city of Richmond. So this is an ambient loop system, which is owned and operated by the municipality. And again, this is to me, this is kind of the current version of what a district energy system should look like. It's similar to some of the 10s that we were looking at a few minutes ago, but this is owned by the municipality. So they installed or they paid for and had us do the installation on this system. Oak Ridge redevelopment, again in Vancouver, BC, brand new thermal energy system that's serving this new development in Vancouver. Again, if you're trying to decarbonize at scale in a district setting, geo is proving to be the best alternative. Large project in LA, the Lucas Museum of Narrative Art that George Lucas is building. It's nearing completion. Another large scale project, kind of a cool building. I'd like to show the picture of this one, but over 700 holes to 365 feet, all located underneath the building and successfully applying geo. Okay, let me skip through to some residential projects. So the flip side of this would be, we're looking at residential master plan communities. We're doing developments like Middlebrook Farms here. Every home in the development is going to have a geo system. It's all going to be zero carbon. Same with the Viridian in Ann Arbor. Same concept, geo as well, under the utility model, under the Orca utility model, Lake Burton. So you could just see all sorts of different communities around the nation that are taking on this approach. Some charter schools or a charter school in Georgia, just south of Atlanta. And then some other residential communities. This is an example of one it's actually in my neck of the woods here. Great project. It's a 55 plus community, so fixed income, and the utility allowed the entire development to go geo, and the energy use on these homes is so low that it's probably going to be on Will's chart there for among the most energy efficient systems. And there you go. That's it. Open to questions, time permitting.
Such a cool graphic with that building transition, really innovative there. Thank you, Stuart. One quick question. So how do you determine different rates for various like home and building sizes?
Yeah, so the primary driver, so we run a financial model. So we own these systems out in perpetuity on our model, and the idea it's really driven by the initial capex on the project. So really it's drilling cost that drives the rate, drilling cost and then design, right? So each project has its own engineering requirements. So for example, if we're on Bedrock, like the question, I know Joselyn's going to be talking about that here shortly. Bedrock is our friend. We love Bedrock. It's highly conductive. The feet per ton you have to drill is considerably or generally considerably less than non-Bedrock. So we look at site conditions, we design the system. So the amount of footage we have to put in per home, that determines how much we have to spend on a per ton basis or per home basis. We run a financial model and we have a certain minimum threshold of return that we need. And that essentially determines our rates. So the rates do vary across the nation, depending on the cost of drilling and really the design of the system.
Wonderful. Well, thanks again, Stuart. That was really great stuff. Appreciate having you on. And last presentation here, Joselyn, and feel free to go right up to the 11:30 mark. We'll skip panelist questions for this one. So yeah, thank you.
All right, perfect. Thanks everyone for making the time here. Really appreciate all those presentations. What Bedrock Energy is focused on is actually answering some of those challenges that were mentioned by Stuart and Will, and just talking about how do we make geothermal even more deployable and even more accessible around the world. So my name is Joss. I'm a co-founder and the CEO of a technology company called Bedrock. And what we do is that we actually bring in automation, robotics, and AI so that the construction of those geothermal systems can be much more accessible and cost-effective. So I'll start with kind of a key point that isn't always brought up because the current industry doesn't leverage this fact as fully for various industry reasons, which is that really, really ambient temperature gradient that was mentioned earlier on, both I think by Will and by Matt, is that it's actually the first half kilometer that really has this really lovely temperature gradient between 55 and 80, which conveniently is just around what we as human beings like in our buildings and facilities. But we don't typically go down to that 1,500 feet mark. Why is that? Because the actual limiting factor in the industry today is what drillers are able to do, willing to do cost effectively. So I'll come back to this depth question. But what we really then focus on is if you step back from just like, if you look broadly at what drillers are able to do and willing to do cost effectively, there's actually a number of barriers to scale that are the reason why only about 1% of HVAC is geothermal, which I think is the poll that Noah and Shannon sent out earlier in this session. And those reasons are broadly these four here, maybe a few others on the margin, but the number one thing is the high upfront cost. Especially without tax incentives, that payback period can be something between 10 and 25 years. We have heard ranges of drilling costs that go from $20 US per foot with the construction of the heat exchanger included, all the way to something I heard yesterday, which was $160 per vertical foot. That is an 8x range in how much that cost can be, depending on varying lithology, varying soil and rock, just around North America alone. So that's obviously the biggest reason why you really have to have innovative financial models the way Stuart and Geotility have brought to the world. But it's also a reason why that we still haven't gotten geothermal outside of really core geographies where there's really high energy costs and therefore larger savings to capture. A couple of the other things that come up often, and this is increasingly true in urban areas, is that you need a lot of space for those geofields. And so that is typically because most drilling is occurring from 500 to 850 feet. Stuart gave the example of the Lucas Museum, which is not too far from where I am right now, and that one was about 365 feet. And those depth constraints that are typically driven by drillers means that if you could actually be going or should actually be going 1,500 feet for temperature optimization reasons, but you actually only go to 500 feet, then you have just expanded the size of your well field by about 3 times. Also in urban areas, drilling deviation, which tends to be somewhere between 5 and 10%, depending on the difficulty of the soil and rock, can create risks in more developed areas where you have subsurface infrastructure, you have the MTA, the MBTA, the tube, and other kinds of other kinds of barriers that would make collision extremely risky. And the final piece around performance is something that I believe Matt mentioned in his presentation about this concern around how do you make sure that the bore field stays in thermal equilibrium over the many, many decades of the lifetime of this system. And today we have often spoken to many engineering firms that will say, yes, we are aware of this risk of thermal creep where the bore field gets too warm or too cold over time, and so we'll oversize the system by 15%, which is going to kind of exacerbate the issue of the high upfront cost. So all of these issues are things that we regularly hear from the industry on why projects don't pencil and turn into geothermal, even though everybody knows it is indeed the most the most energy efficient form of HVAC. And at Bedrock, our goal is to say, how do we overcome these barriers to adoption so that geothermal can go from 1% of HVAC to 10, 20% of HVAC and drive greater energy resilience and sustainability. So what we do at Bedrock is our technology stack really focuses on how do you drill faster? If you drill faster, and we have already demonstrated faster drilling speeds of about 3 to 6x, depending on the difficulty of the soil and rock, time is money. And so when we're going faster, we are also bringing down the cost of that construction. And doing so, no matter what kind of soil and rock, means that we don't have these crazy ranges of costs from $20 to $160 per foot, but that even in those most difficult conditions that we're actually coming down on that bottom end of the range. Being able to go deep confidently also enabled us to reduce the amount of bores that are needed. And that is very important in retrofit conditions in kind of urban developed areas where the space for putting in a geothermal field is much smaller. We are also uniquely able to do real-time 3-dimensional monitoring of the drilling path. And so if you're in an urban area, in a place where you're really conscious of your neighbor's property lines, we are actually real-time sensing and managing that drift so that there is absolutely no risk of collision or concern. And then finally, in terms of the question of how do you make sure the subsurface is able to handle any kind of thermal imbalance, we are applying physics-based subsurface modeling constantly through the drilling process. So we are actually potentially gathering 1 million times more data points than typical drillers in order to continue updating a thermal profile of the ground at high data resolution and giving that to our engineering partners to make sure that the subsurface is indeed the optimal design for that building's energy load. All of this probably sounds somewhat fancy. And so the question is, where does it come from? And the answer is that we really bring together a technology team that comes from many industries, the top tiers of oil and gas technology. My co-founder was a chief scientist at Baker Hughes, having hundreds of patents, inventions, and papers related to oil field technologies. We merge that oil field technology with oil field operations, but then also Silicon Valley kind of big tech and startup innovation. And then we combine that with real estate and construction expertise to deliver something that works really well for developers like Stuart's team, for manufacturers, dealer distributor reps, and then also, of course, for engineering firms and general contractors that are looking to meet their clients' sustainability goals. And so what exactly is the tech stack that this team has put together? What you see here is a design construction platform based on a concept called coiled tubing. What this means is that we actually have a 3,000-foot steel pipe that is used for the drilling process. Unlike every other drilling equipment in the geothermal industry, we do not stop and go to a standstill every 10, 20 feet in order to fasten on another pipe. We just have one single 2,000, 3,000-foot pipe that goes continuously into the ground, creating the hole, and then also pushes the heat exchanger down really, really consistently and makes sure that the completion process in that construction procedure is done seamlessly. Doing so means not only that we're faster and more and require fewer people on site, therefore making us more efficient, but importantly, we have our own proprietary sensors at the very end of this contraption so that we are reading the ground during drilling. We're gathering that 1 million data points from a single bore field. Like every bore field, we're just gathering foot by foot, dozens of data points. That enables us to apply basically a form of computer recognition. And that computer vision then allows us to make decisions no matter what changes there are in the subsurface rock and soil, so that we are drilling and constructing these systems indeed 3 to 6 times faster than other folks who might struggle with depth, struggle with water production, struggle with unconsolidated formations, and so on and so forth. At the end of the day, all of this is about driving down the capex of those geothermal fields so that developers and their partners can have the highest ROI because of low capex and good energy savings outcomes. We have been doing this for a few years now, and so some of the case studies where we've really already been able to show that have ranged from Texas to Colorado to Utah, and we're expanding our footprint into the Northeast, into New York and Massachusetts later this year. And in these places that we've already worked in so far, we have done retrofits in these really tight areas where we had to shrink the geothermal field size by about 3 times. And in doing so, made geothermal possible where it wasn't otherwise possible. So here's an example retrofit with a really large real estate owner where conventional practices in the Texas area would have required the blue box of geothermal, which obviously doesn't work since the building is here and the neighbor is here and there's a natural gas pipeline here. And so what we actually did was, by going deeper, we were able to fit it into just the orange box. And we were able to do all of this while the building was occupied Monday through Friday, and keeping noise, keeping mess, and just overall keeping disruption really, really low because of our machinery stack. So that's one example of making retrofits more viable. In a new construction situation, this was from last winter. We are also showing that in really difficult locations where other folks might say, well, this is not nice, clean, consolidated granite, which I think either Matt or Will mentioned in their presentations. Other folks might think that only certain lithologies are viable and cost-effective and easy to handle for geothermal. We actually can do any kind of subsurface formation. So in Utah, this really difficult, Rocky Mountain glacial till, there were experienced drillers that were taking 4 or 5 days to drill 500 feet, and we're able to do twice that in less than a day. So all of this is just small case studies to say that what Matt and Will have been pushing into the world, what Andrew has been, telling the story of at the highest levels of government, and what Stuart has been developing, all of this can and should be more scalable all around the world, but so often it's that subsurface construction that is the limiting factor. And in making that more cost effective, we're able to drive adoption up, reduce those logistical barriers to installation. And then overall, just most importantly, by bringing down the costs of these geofields, we make them into a distributed energy asset that is just simply the most cost-effective and resilient form of distributed energy. So what you see here is a chart that says, look, if you are developing a project where the utility is saying, hey, you can't have the power you want for 4 or 5 years because we are so power grid constrained across so much of the United States. And you're thinking, well, all right, if I need to do a microgrid of some kind in order to get the power that I want to operate my building, operate my campus, or I just want to do so for resiliency reasons, well, gosh, solar and storage could be somewhere between, $3,000 and $5,000 per kilowatt to produce it behind the meter on site. But instead, if a geofield is more cost effective to build, then your per kilowatt reduction could be something closer to $2,000, $2,500 per kilowatt. You would obviously go with the more cost-effective option, at least as part of your energy strategy. And that is only possible if you can bring down the cost of that construction of the geothermal asset. Another way of looking at this is that, by bringing down that system CapEx, you just get faster payback periods. And so, our goal is just continuously bringing down the cost of this orange piece, which is what you see here. It's the cost of the geofield on top of heat pumps. And that orange piece, the lower that cost goes, the better and more broadly people can access a 5-year payback period or even less, which is where you really see those like, double-digit IRRs that are so important for return on capital. So, I think I'm at the hour and could probably answer one question, but ultimately, we are here to make what everybody else on this panel pushes for and develops much more accessible to everybody here in the audience.
Joselyn, thank you so much. Awesome presentation. A bunch of questions coming in here, so I'm just trying to find one. It seemed like there are a few questions about pumping and pipe costs getting a lot higher after like 500 or 1,500 feet. It seems like y'all are combating that though pretty well, right?
Yes. So a lot of that construction cost has historically gotten more expensive after 500 feet. And that's why most drillers will tell you, I can't go past 500 feet. Can't is an interesting word. It's just because it's pricey. And so the reason they can't is because the deeper you go, the more soil and rock variation is going to it's going to add up in terms of all the challenges. And that just gets expensive if you don't know what's going on. It's kind of like if you were driving a manual car across hills and off-roading and doing all of that, well, the more crazy your off-roading is, the more important it is that you can see where you're going and see what you're doing. But imagine someone blindfolded you. That would be terrible. You wouldn't
Totally.
do very well. And so we're essentially saying, yep, let's let people off-road, metaphorically, at 500, 1,000, 1,500 feet, but see where you're going and then add AI and automation.
Love the analogy there. That's awesome. Well, yeah, as you said, we're at time, so we're gonna skip the panel questions today and just wrap up here. And I think we got a lot of great questions answered though anyway throughout the presentations. And thanks so much for to the audience for the great interaction and questions too. And obviously just a huge shout out to our panelists today. Really great discussion from everybody. Love the presentations, and I think as Shannon, my colleague, mentioned earlier, this is being recorded, so we can certainly send it out if folks that missed it or if you want to review something. And we'll also send a PDF version of the slides out as well. So you'll have all that information handy. And yeah, thanks for attending. This was great. And yeah, thank you, panelists. Have a great rest of your day.